real numbers Jadi kalau root semua, that's why bila kita buat root locus, we want to look at the roots. Where are these roots? Okay, jadi kalau semua roots are complex, this is what happen yang number B ni This is what happen. So it is called undamped, where your system tak boleh pergi. Dia macam inilah. Dia sepatutnya kena, when we put the step input, dia kena response kepada step. Right? Walaupun mungkin kat sini ada overshoot sikit, okay, mungkin dia lambat, rise time, settling time and all that. And then yang number C adalah overdamp. Overdamp ni happen when all the roots are real. So the atas tadi when all the roots are complex, number bawah ni when all the roots are real, dia tak sampai kepada the input yang kita set. So this is called overdamp. When zeta more than 1. Undamped is when zeta equal to 0. So that's why we really want to look, kalau boleh kita nak the system to response lah kepada whatever the input that we put into the system. Okay, so in order to analyze the systems, that's why we have all this information yang kita boleh nak tengok lah. We want to look at the rise time, how fast the system responds to the input, peak time, okay, and then bila masa dia pergi peak tu yang dia overshoot sikit tu, and then time dia settle, okay, sebab dia akan peak, dia akan overshoot sikit, and then dia ada gerak-gerak macam ni kan, okay, and then dia settle. So settle means go to the input that we set. So these are actually the transient response yang you all belajar sebelum ini, dan now kita nak tengok, we want to relate with the roots. So itu sebabnya ada root locus. Root locus, kita tengok root locus, and then kita we relate with the transient response that you learned previously. So you know the concept now, class? Faham jadi janganlah, itu sebabnya kita dah susun syllabus control tu dah cantik lah. You buat equation, you understand, you getting the mathematical equation, and you put the input, and then you look into the response, and then you analyze further using either the transient, and then nanti kita akan buat lah MATLAB and so forth. So transient response of a dynamic system is closely related to the location of the poles. Okay, poles located on the right side of S-plane. Okay, jadi kita ada S-plane. Since I cannot catat kat sini, aduh tak puas tu. Okay, so if you have the S-plane yang imaginary dengan real axis tadi, if it is on the right side of the plane, it will result with unstable system. Itu kita belajar masa buat stability. All poles are negative real numbers. The output will be overdamped. A complex conjugate poles, a damped oscillating system yang kita buat tadi. Kalau dia semua kompleks, dia akan oscillate sahaja. Dia tak pergi kepada input yang kita hendak dia pergi. Okay, so poles on imaginary axis result in sustained oscillations. Okay, so figure here, now you can you see, class? I have the S-plane as well as the graphical response of a system. Nampak Hello?
Nampak, Doktor.
Page 7 So this is actually what we did lah. Kita tengok response. So kalau postnya di sini, okay, for example, kita tengok yang top left. Okay, top left. Top left, betul Okay. So top left ni, this is kita punya poles, which is complex conjugate. So complex conjugate pair of poles, negative real parts, decaying oscillation, they oscillate and then settle. And kalau negative real poles, exponential decay, and then kalau dia positive real poles, increasing without boundary, and then kalau complex conjugate pair of poles, positive real parts, so growing oscillation. So these are the characteristics. And we know that on the left-hand side of the S-plane, the system are stable, whereas if the system are on the right side of the S-plane, the system actually not stable. So that's why bila kita buat Ruth table tu, kita tengok point yang dia point the connected dia panggil intersection. Okay, intersection point dekat imaginary is actually to show us the boundary of stability. Kan kita kata okay stable, system will stable from that point. Bila kita dapat K, system will respond within this range. Okay. So okay, now we understand all this, the concept of transients, and then the concept of the roots, poles, and zeros on the S-plane. Now determination of the damping ratio, damped and undamped natural frequency, as well as time constant. Actually from the root locus, sebab kita dah belajar tadi, if we get the transient response just now, okay, so from the transient response, it will tell us so many things lah, rise time, peak time. What about tau, time response? Bila time response, ingat tak berapa persen of the final value is called time response, class? Tau. Oh, korang ni tak habis satu semester lagi dah lupa kan? Tau tu bila berapa persen? Alamak, saya cakap seseorang ke ni?
63.
63%. Okay, so 63% kalau katakan 100 kat sini, so kita cari value 63 and then this is the time response. Time response sebenarnya adalah describe the system lah. Okay, so daripada situ kita boleh dapat time constant, time response, time constant and so forth. Okay, so actually there is another way of finding that from our root locus that we sketch or we buat sebelum ni lah. So the value of zeta, omega n, omega d and t using contour distance on S-plane. Saya tulis ni. Contour n tertinggal. Contour parallel with real axis represent omega d. Contour parallel with imaginary axis represent 1 over t. Jadi daripada imaginary axis tu 1 over t. So dari situ kita dapatkan value from the graph and then we can get the t. Distance between the straight line and imaginary axis, value of 1 over t equal to zeta omega n. Contour of the circle represent omega n. Contour of radian represent zeta. Okay, so apa maksud dia? Bila kita buat S-plane, okay, so these are the value. Dah ada juga yang tertinggal ni. Kat bawah tu actually this one, yang bawah ni yang X ni kotak tertinggal ni actually omega n, zeta omega n which is 1 over t. Kenapa dia hilang? Ni. Zeta omega n 1 over t adalah distance between straight line and imaginary axis. So sini ya. Okay, and then constant line 1 over t. And then this is the, kita fahamkan dulu what it tells us and then we apply that into the example. So kita tahu kalau ada, let's say kita ada beta daripada zeta, okay. So kita buat satu line di sini. The intersections, okay, will tell us about the value of k later on. Okay. So sebagai contoh, okay, so let us look at this example on the transient response characteristic of a dynamic system. So dia ada characteristic equations dia, maknanya meaning that the poles of the system, let's say we have s square plus 2s plus 2, so the poles of the system are -1 plus j and -1 minus j. So kita ada dua poles. Okay, so the poles position on the S-plane will tell us about omega n. Okay, so bila kita buat poles kita di sini, sebab saya tak boleh tulis lah ni, omega n here. So from these poles kita, this is our pole, sorry, this is our poles. So bila kita buat line di sini, okay, from the poles to the origin, tells us about omega n. Okay, so the y-axis di sini and the real axis, okay, tol sesebab omega D dengan T. Okay. And then kalau beta di sini, beta makna the degrees here will tell us about zeta. So kalau kita tahu beta di sini, so zeta kita adalah 0.707. So meaning that kita dah buat tadi kan, kalau zeta tu between 0 to 1, it is apa tadi kelas? Yang ni lah. So itu yang kita nak tengok. So zeta between 0 to 1, dia punya response will be like this. Okay. So that is the relationship between the poles and zeros and the transient response characteristic values. Any questions so far? Okay, kalau tak ada, kita teruskan. Tadi kita kata we have our system S square plus 2S plus 2. So now let us relate dengan the apa tadi the equation for second order system. So kita tahu equation of second order system macam gini. Standard second order system. So from here we know the omega n. Kalau kita tak buat root locus lah. So meaning that omega n kita 1.41. Sama tak dengan tadi? Yes, 1.41. This one ni menggunakan root locus lah. Okay, and then what about the zeta? 0.707. Okay, yes. Because ini satu beta kita 45. So cos 45 will be 0.707. So sama sini. And then what about omega D? Omega D equation dia adalah omega n square root 1 minus zeta square 1.41. Okay. From these systems also we can calculate the percent overshoot. Okay. So you all belajar juga I assume to calculate the percent of overshoot. Yang mana tadi? Dekat sinilah. How much the system overshoot sikit. Maknanya kalau sikit lagi bagus lah kan. So dia tak adalah overshoot banyak sangat. Katakan kita nak set room temperature kepada room temperature usually about 25 degrees Celsius. Okay, bila masuk aircon kat bilik kan. So kalau dia overshoot pun dia overshoot sekejap. And the time tu kalau boleh kita nak sekejap sikit sahaja. And then the overshoot pun sikit. So that ini saya bagi sampel example yang simple. Is the actual application usually in the factory and so forth lah. Kalau dia punya apa tank dia dan sebagainya. Okay. So that one I relate. One is with the Allah. Sabar cikgu. Okay, satu I relate with the finding the transient response value or transient response characteristic using the root locus, and another one is using the equations that you learned before. Okay, so macam ni tadilah kalau percent overshoot kita ada this formula. So once we get the formula of of the zeta and all that, we can calculate the overshoot and the other related values. Okay. Now, class, to understand further, let us look at example 4.13 in my textbooks, in my book. Okay. So the question is, sketch the root locus of the feedback system shown. Yang ini. Ada tak kita dah buat yang ni? Belum. So far S4 dengan 10 belum lagi ya. So okay, I start with a very simple one without zeros and tak ada complex lah. Tak ada complex conjugate poles. So all three are poles and then the real value, tak ada complex. Okay. So construct root locus using the 9 steps. Okay, buat step by step. And then choose the value of K. Once kita dah dapat kita punya root locus, from the root locus, choose the value of K such that the damping ratio does not exceed 0.5 and the time constant is less than 1 second. So you buat dulu step 1 sampai 9, we have a lot of time. Okay, step 1 to 9, and then from your root locus diagram, kita ada condition di sini. What does it mean damping ratio does not exceed 0.5 class? Hello? What does it mean damping ratio does not exceed 0.5? Kita tahu tadi damping ratio, from damping ratio, what can we get? We can get beta. Okay? Damping ratio dah dapat, mana beta inverse cos damping ratio. So bila kita dapat data angle with using the compass ataupun you boleh juga calculate dengan menggunakan graph tu . So from that angle, kalau damping ratio 0.5, angle dia lebih kurang berapa? Cuba calculate. Kelas inverse cos. Alamak, saya cakap seorang-seorang ke ni? Hello? Damping ratio 0.5. So degree berapa tu?
Degree, 60 degree.
60 degrees. So from your root locus, you buat 60 degrees and then you buat line. Okay. From that line, you will get the intersection of the condition of the damping ratio with your root locus. Point di situ, from that point you can get your value of K. Remember I taught you about the angle and the magnitude characteristic equation kan. So 1 plus KGH1 plus KGHS equal to 0. So from there you have the distance and you can calculate K. Okay, tak apa, kita buat dulu root locus and then kita buat sudut 60 degrees just now. And then we try to locate the point of intersection. And another one, dia ada dua condition. Satu, damping ratio dia does not exceed 0.5. And then another one is time constant. Time constant tadi apa kelas? Yang ni. Okay, so another line, maknanya you all buat dua line. Satu line for the damping ratio, another line is for the 1/T. And then kita tengok bagaimana . So I give you about 15 minutes cukup tak nak buat untuk root locus. And then I will open the Jamboard and then I'll give the link in the WhatsApp group. So please go to the Jamboard. Okay, saya buat sekarang lah. Jamboard. So nama dia root locus and transient. Okay, and then I will make it public. Share with UTM, copy link, and then try to put your root locus inside this Jamboard and then kita move forward lepas tu kepada finding the K based on the two condition just now, the damping ratio 0.5 and then the time constant equal to 1 . So now I share. Saya dah share tadi kan? Go copy link. And then I share this. Locus and the panggil here is transient set point design. Okay. So soal buat dan 10-15 kalau nak minum mungkin ada yang tak sempat breakfast and so forth. 10-15, 10-20 kita discuss on that. Okay? Okay class, are you clear?
Okay, doktor.
Okay, so buat dulu.